Hello, I welcome you all in this presentation. This presentation is related with the heat affected zone and the weld thermal cycle, and in this presentation I will be talking about the heat affected zone characteristics related with the precipitation hardening metal systems. So, in the last lecture I have talked about the work hardenable metal systems. So, in precipitation hardenable systems, to understand the heat affected zone and the weld thermal cycle related aspects, it is necessary to understand what the precipitation hardening is and how the metal systems are strengthened. So, the requirement for precipitation hardening is that the solubility for the alloying elements must increase with the temperature. So, the alloying elements, say this is the metal A and the metal B, and whenever a particular fraction like say 4, 10, 15 etc., the B is incorporated in A, we will see that one particular Solves line, and this Solves line maybe in generally is found to be like this. There can be different Solves lines like this, which shows that the temperature above which the solute will get dissolved. So, the 4% of the B will get dissolved above this temperature, 10% B will get dissolved above this temperature, and here it will get dissolved above this temperature. So, Solves line is basically, or Solves curve shows the relationship between the temperature and the concentration of the alloying element here, and what it shows that as there is increase in temperature, the solubility of the element in the matrix, alloying element in the matrix increases. So, what we do first, say for the alloy having alloy A, matrix A having 10% of the B. So, this is an alloy just for example. So, here this alloy will be heated above this temperature curve on the Solves line, so that we will have homogeneous alpha system, homogeneous solid solution is formed. So, we go well above this temperature, so to have the homogeneous solid solution. So, this one is called solutionizing. So, heating above the temperature, heating at the temperature above the Solves line helps to achieve the homogeneous solid solution. This step is called solutionizing, and then once the homogeneous solid solution of the alloy is formed, then we will be quenching it fast. So, it is quenched by cooling rapidly in the water or oil. This is called quenching. So, since during the solutionizing we have got uniform presence of the alloying element in the matrix in form of the solid solution, which may be interstitial or substitutional, and rapid quenching this solid solution when quenched rapidly forms the supersaturated solid solution, because it does not allow any diffusion to take place, and the solutes will be retained wherever they are present. So, this in turn results in the supersaturated solid solution, wherein the solute will be present in the matrix much more than its capacity to accommodate, means above the solubility limit. So, the alloying elements present at room temperature in the limit above its solubility limit, and that is why it is called super saturated solid solution. This supersaturated solid solution then subjected to the aging. The aging can be at the two levels. The supersaturated solid solution subjected to the aging means it will allowed to hold for some time. So, if this aging is done at high temperature, means artificially heating is done to have the high temperature exposure, means aging at a high temperature is termed as artificial aging, and this is typically termed as T6 treatment or temper condition. So, during this exposure at a high temperature, which is normally say for aluminum alloy is 150 to say 230 degrees centigrade, it may be different for the different metal systems. So, during the high temperature exposure, supersaturated solid solution starts forming the precipitates uniformly in the matrix. These precipitates, depending upon the kind of alloy or alloying elements, it will form the different types of the precipitates. These fine precipitates, which are basically, if they are coherent, these can be coherent or non-coherent. So, the coherent precipitates help to strengthen the alloy significantly as compared to the non-coherent precipitates. So, in this way there are 3 steps in precipitation hardening of the metal systems. One is solutionizing to form the homogeneous solid solution, second is quenching to form the supersaturated solid solution, and third is aging. Aging may be done at a high temperature for artificial aging, or it may be done at room temperature for natural aging. So, artificial aging is normally termed as a T6 temper condition, while the natural aging is done by just holding the quenched samples at a room temperature after solutionizing, is termed as a natural aging, and it is given the temper T4. So, T4 for the natural aging and T6 for the artificial aging. So, as far as the welding is concerned, when the precipitation hardened systems like this, say it is a aluminum copper alloy, the common alloys which are precipitation hardened is the aluminum magnesium silicon system or aluminum zinc magnesium system. These are the common precipitation hardenable systems. Copper alloy CuAl2, Mg2Si and MgZn2. These are the kind of precipitates which are formed in these 3 types of the precipitation of hardenable alloys, and when these are non-coherent, they result in somewhat marginal increase in strength and hardness, while in the case when they are coherent, depending upon the temperature and exposure conditions, they will be resulting in the maximum increase in strength and the hardness. So, coherent precipitates always preferred over the non-coherent, and conditions are developed in such a way that the system is having the coherent precipitates. So, the typically we will take one system just to explain the way by which the properties are affected when the heat is applied during the welding for the change in the properties of the heat affected zone. So, considering this, we will take up the one typical aluminum copper system alloy just to explain. So, here if you will see, the aluminum copper systems have the various kinds of the lines, solvus lines for the different phases like this. So, here as a function of time, and here in the y axis we have temperature. This is what we can see clearly from these diagrams. So, for the aluminum copper systems, this is the typical phase diagram for aluminum copper systems. Solute, that is the copper, in x axis and the temperature in y axis. This is the solvus line, and here it indicates that when first heating is done in this alpha region, so that solutionizing takes place, then it is quenched back quickly. So, quenching results in the supersaturated solid solution, and thereafter Third step is the heating artificially at about 200 degrees centigrade, so that the precipitates can be formed. The different types of the precipitates are formed in these systems, and that is what we can see. Supersaturated solid solution, in course of the aging, it will be resulting in the GP zones, Guinier, that is called Guinier Piston zones, the theta double dash, theta dash and theta. These are the different precipitates. The Guinier Piston, it is also called GP1, theta double dash also called GP2, and the theta dash phases, all these are metastable phases. Theta is the equilibrium phase, that is the CuAl2, and it has the BCT crystal structure. So, if you will see this diagram, the Solves line for the GP phase, Guinier Piston 1 is the minimum. This is the this is Solves line for the GP phases, and then theta double dash, then theta dash, and thereafter then one Solves line for the aluminum and copper system, where the homogeneous solid solution of the alpha or the alpha aluminum is formed. So, what it shows that the GP theta double dash and theta dash. So, this is what we can see, GP theta double dash and theta dash. It shows the temperature, sorry, here we have the concentration of the copper. So, copper and the temperature. So, here it occurs around say 150 to 200 degree centigrade, then the 250 degree centigrade, and likewise some higher temperatures. So, if we see the GP and the theta dash phases will get dissolved as per the concentration of the copper, they will get dissolved above the particular temperature, say 200 and above. So, the GP and the theta double dash phases are the metastable, while the theta is a stable or equilibrium phase, and similarly theta dash is also unstable, and above the particular temperature these get dissolved. It is always desirable to have a particular kind of phase, so that the maximum strength can be achieved. So, what we can see, the different phases are formed after this during the precipitation or during the aging, and some of these phases are coherent, some of these phases are non-coherent, and accordingly they will have effect on the hardness. At this is the typical photograph showing the precipitates which are formed. These are very fine in size, say the dimensions are in like say 10 of the angstrom to the 100 of the angstrom in the thicknesses, and the diameter of these precipitates can vary from say 500 to the 2000, 3000, 4000 angstrom. So, these are very fine in size. Normally these are not resolved under the optical microscope. So, transmission electron microscopy is used for this purpose. If we see this diagram, what it shows, that as a function of the time how the properties or the hardness of the particular alloy varies in course of the aging. So, if we see this diagram, typically here in x axis it has the time, and in y axis it has temperature. So, time is about the aging time, and in y axis it is the temperature. So, how the property change takes place when the exposure is given at the different temperatures. So, in one particular case like say it goes in like this, here when the exposure is at 130 degree centigrade, and when it is done at a higher temperature, then peak is achieved earlier, like say it is 190 degree centigrade. So, what it shows, for the peak hardness it takes longer as compared to the peak hardness at the high temperature, and the different phases which are formed, like say the GP1, GP2, and here thereafter non-coherent phases are formed once the overaging starts. So, what we can see here, initially with the aging there is a formation of the GP1 and then GP2 phases, and if this high temperature exposure is continued for longer period, then the non-coherent phase formation results in the drop in hardness. So, this one is termed as this is the hardness, not the temperature. So, it is the hardness. So, if the exposure is given at 130 degrees centigrade for the different increasing periods for the different aging times, we will see that initially the GP1 is formed, then GP2, GP2 will result in the maximum increase in hardness, and thereafter due to the formation of the non-coherent phases, hardness starts dropping. So, this is the stage when we need to stop for achieving the maximum hardness and strength. Similarly, when the high temperature exposure is further higher temperature exposure is given, then the peak hardness is achieved in much shorter period as compared to that at low temperature. So, always target is to have the GP2 phases in the maximum amount, so that the maximum strength and the hardness can be achieved. So, and how do these phases offer the strength? The lattice strain is very severe around the coherent phases like this. So, this is the this schematic diagram shows the supersaturated solid solution, and when the aging is achieved or when aging is performed, coherent phases result in the distribution of the solute in the matrix like this, and the distribution of the solute in the matrix is like this for the non-coherent or incoherent phases. Coherent phases result in the maximum strain around the region where these are present as compared to that of the incoherent phases. So, that is why the maximum strain around the coherent phases result in the increased barrier for the movement of the dislocations, and which in turn increases the strength and hardness of the alloy significantly, while the strain around the non-coherent phases is very less, and that is why barrier to the movement of dislocations is very limited, and which in turn does not result much increase in the strength and hardness. So, according to the type of the phases which are present, like if the non-coherent phases are formed, then strength and increase in strength and hardness is not much as compared to the coherent phases. And this is what is observed, that after the peak hardening or after the peak strength exposure to the exposure of the alloys at high temperature for much longer period causes the over aging due to the formation of the non-coherent phases, and that is why reduction in strength and hardness is observed. So, the different types of the precipitation hardenable alloys and the kind of phases which are formed in case of the aluminum alloys, that is what has been shown in this diagram. Now we will see the kind of behavior which is observed as a function of the time, aging time and the strength. Normally the trend is like this: when the strength in y axis, strength on hardness in y axis, aging time in the x axis, and what we will see that if the temperature is high, then this is observed very quickly, otherwise it takes longer time like this. So, what we can see here, if this is the high temperature, somewhat low, medium and low temperature. So, low temperature exposure results in the higher increase in the strength, but after a longer time, while medium temperature results in the means peak hardening occurs after a very long time at low temperature, while that in case of the medium temperature it takes shorter time, and for the high temperature it takes very short time. So, it is important that if the temperature of the exposure is high, then the softening will start much earlier, while if the temperature of the exposure is low, then it will take long time for the softening to occur. This is important with respect to the weld thermal cycle. So, the zones of the weld which are very close to the fusion boundary, like this, the zones of the weld which are very close to the fusion boundary, they will be subjected to the high temperature as well as for longer period, and that is why we will be getting the softening or over aging much earlier as compared to the case when the point is located away from. The points which are located away from will be experiencing the lower peak temperature for shorter periods. So, both these things are favorable. It will be having the minimum effect of the over aging, or over aging effect will not be that apparent and visible. So, the over aging the formation of the non-coherent phases or the dissolution of the phases will primarily be observed next to the fusion boundary. Since the precipitation hardenable alloys are strengthened by the precipitates, so with the application of the heat, like say this is the weld with the heat the weld joint is formed, and next to the fusion boundary we have 1, 2 and 3 points. Obviously, each will have its own, this will have the highest temperature and for longest period, while the point 3 will have the minimum peak temperature and for very short period. So, what we will see that at the point 1 there will be the dissolution, coarsening and coarsening as well as the formation of incoherent phases. So, fine phases either they will get dissolved or they will convert into the incoherent phases, or their coarsening will take place. So, all these phenomena will be leading to the softening of the precipitation hardenable alloys in the zone next to the fusion boundary, while its effect will be less away from. So, if we will see the hardness variation from the fusion boundary, hardness will be minimum next to the fusion boundary and then it will keep on increasing. So, hardness of the zone 1, hardness of the zone 2 and hardness of the zone 3. So, we may have like this is for the base, if here this is the hardness curve and this is the distance from the fusion boundary, So, the zone which is very next to the fusion boundary will be experiencing the maximum dissolution, coarsening and formation of incoherent phases, and that is why we will have the very low hardness, while as the distance increases the extent of dissolution, formation of incoherent phase precipitates and the coarsening will be limited, that is why somewhat higher hardness, then somewhat more hardness, and then it is corresponding to the base metal. So, this is the typical behavior which is observed next to the fusion boundary. What we get in like the hardness is minimum and then it increases. So, this reduction in hardness is called the softening of the heat affected zone, and this softening is invariably observed in the weld joints of the precipitation hardenable alloys. So, now if we try to relate it with the heat input and other conditions related with the welding, then what we will see with the increase in heat input, simply the effect of heat input is what, say the plate is welded using 2 kilojoule per mm heat input, then the weld zone size will be this much and heat affected zone is this much. And if the same thing is welded using 3 kilojoule per mm, then our weld zone will be wider because of the more heat input and the heat affected zone will be further wider. So, heat affected zone, since if the width up to which increase in heat input increases the width up to which the temperature rise above a critical temperature increases, which in turn increases the width of the heat affected zone, while this width is limited. So, basically HOZ size is directly related with the amount of the heat input. More is the heat input, wider will be the heat affected zone, larger will be the cross sectional area of the weld, and this in turn will have the more adverse effect. So, if we try to replicate this in terms of the hardness variation from the fusion boundary to the base metal side, then increasing distance from the fusion boundary will be showing that the for 2 kilojoule that variation in hardness is like this, while say 2 kilojoule per mm hardness variation, and the extent of the hardness loss will be much more for the 3 kilojoule, and this will see this is the extent of the softening which will be occurring in corresponding to the region which is very close to the fusion boundary, and then somewhat more and so means this wherever the drop in hardness is taking place, that will be the part of the heat affected zone, and increase in heat input will simply be increasing the width up to which the softening is taking place, and that in turn will be weakening the material and will be leading to the reduction in strength of the metal system. So, this is what is about the effect of the weld thermal cycle. This is what we can see here when the material is in the precipitation hardened condition, like in the base metal condition, it has a large number of the precipitates. As we approach towards the fusion boundary, the number of precipitates have reduced because some of them will get dissolved, and as we further approach towards the fusion boundary, these have got almost completely dissolved. So, this dissolution is also termed as a reversion. Full reversion is taking place close to the fusion boundary, leading to the maximum reduction in the hardness, while the partial reversion or the dissolution will be taking place away from the fusion boundary. So, somewhat more precipitates can be seen in the heat affected zone. So, it will have the somewhat higher hardness and maximum hardness in the base metal. So, this is what it reflects in this diagram also. In the zone 1 corresponding to the next to the fusion boundary experiences the maximum softening. The zone 2 is having somewhat more precipitates than zone 1. So, this diagram shows the location 1 weld thermal cycle experiencing maximum temperature for longest period. So, it will have the complete reversion or complete dissolution of the precipitates, will be leading to the minimum hardness, while away from this what we can see somewhat less reversion is taking place. So, the hardness will be somewhat more as compared to the location 1. So, increasing number of the precipitates as we are moving away from the fusion boundary, and the reduction in peak temperature, reduction in the time for which high temperature is retained. So, the reduction in temperature and the for shorter period of a particular temperature will be leading to the limited reversion, somewhat more reversion and full reversion, and this in turn will be leading to the reduction in hardness of the aluminum alloys or the precipitation hardenable systems next to the fusion boundary. So, now I will conclude this presentation. In this presentation I have talked about the strengthening mechanism of the precipitation hardenable alloys, and how the strengthening mechanism can be related to the heat affected zone properties when the metal systems are welded. So, the application of the heat in these alloys basically causes the three things. One is the dissolution of the precipitates, also called reversion, coarsening of the grains, and third is formation of the non-coherent precipitates, and these three phenomena, these three effects result in the reduction in the hardness and the loss of the strength of the metal system, which in turn is also termed as the softening of the heat affected zone in precipitation hardenable alloys. So, now thank you for your attention.